So, good evening, everyone. This is lecture number 12 in the JEE Advanced series. And in this particular lecture, we are going to deal with electromagnetic induction, one of the most important topics because it encompasses everything that we have studied till now, starting from electric current to magnetic field. And this is the penultimate chapter in that series. After this, obviously, comes alternating current, which is also similar. But let us first deal with this electromagnetic induction. I'm sure you have a certain idea about electromagnetic induction, yes or no?
Yes, sir.
Okay, now how do we start this chapter traditionally is by the definition of electromagnetic flux or magnetic flux. I'm sure you have an idea about that. What do you mean by magnetic flux? Yes or no?
Sir?
Magnetic flux is something like electric flux. Do you know this?
Yeah.
Electromagnetic flux or magnetic flux? The number of magnetic field lines which are crossing a particular area in a direction which is perpendicular to that area, that is known as magnetic flux. Do you know this?
Yes, sir.
So magnetic flux, if I have to write, magnetic flux Fm is integral of B dot ds, where B is the magnetic field and ds is the small area. I'm sure you know this, yes or no?
Yes, sir. Yes, sir.
Okay. Okay, and we also know that this magnetic flux is a scalar quantity. It can be positive, it can be negative, it can be zero depending on the angle between magnetic field and area vector. If the area vector and magnetic field are at acute angles, flux will be called positive, which we call as the outgoing flux. If the angle is obtuse, we call it negative flux, which is the incoming flux. Yes or no?
Yes, sir.
Now, at this point, we are ready with all the four formulae, and I'll just let you know all those formulae which are Maxwell's equation. The first formula that we had seen was integral of E dot dl. Do you remember this integral of E dot
Yes,
dl?
sir. Yes, sir. Yes, sir. Integral of E dot dl
Over a
equal
closed
to.
loop, integral of E dot dl is always equal to 0. Yes or no?
Yes, sir. Yes, sir.
Then we had integral of E dot ds, which was your Gauss law, yes or no, over a
Yes, sir.
closed surface, and that was always equal to charge enclosed divided by epsilon naught, yes or no, beta?
Yeah, yes, sir.
These are the two integrals for electric field. Similarly, we have two integrals for magnetic field as well. I hope you know this. So what is the integral of magnetic field over a closed loop? Line integral of magnetic field over a closed loop. That is what we did in the previous class. It is equal to what? That was known as Ampere's law. Do you remember Ampere's law, beta? Ampere's circuital law.
Ampere. Are amperes la ra?
It was equal to mu naught
Mu
into
naught by
current
2 pi.
enclosed. Remember this?
Yes, sir.
Okay. Similarly, if I take the surface integral of B dot ds over a closed surface, this will be equal to 0. If I have a closed surface and if I find out the magnetic flux over that closed surface, it will always come out to be 0, because you remember magnetic field lines are always in closed loops. Magnetic monopoles do not exist. If there is a north pole, there must be a south pole. So either you are enclosing both north and south pole, or you are not enclosing anything. If you are enclosing both north and south pole, your flux will be 0. If you're not enclosing any north or any south, your flux will be 0. Do you remember this? Yes or no?
Yes, sir.
Okay, that was electromagnetic induction, flux linkage. I hope you know what is the
Drop here.
what is positive flux and negative flux. Let me just start with the very simple question based on magnetic flux. And remember, if the magnetic field is constant, instead of writing it as integral of B dot ds, we can simply write it as B dot A or B dot S? Yes or no? This is a very simple question. Just to give you a brief introduction of what is magnetic flux, you have a loop of wire which is given as whose area vector is given. It's a three-dimensional area vector, and it is placed in a magnetic field, and you are supposed to find out the flux through this closed loop. What will be your answer be? How will you get your answer? Remember, the most important thing here is magnetic field is constant, so you can easily find out the flux of this magnetic field through this area. Yes or no?
Yes, sir.
What would be your answer be? This is a straightforward, simple question. What is your answer? Remember, every question that comes in a JEE is a simple one. Complicated questions don't come. Yes, what is the answer for this one? Magnetic field is given, area vector is given. What you got to do?
1.5.
Yes, you just need to take the dot product of magnetic field with area. If you take the dot product, only the J component will remain. 0.3 dot with 5J. Other component will cancel out. It will become 0. So the answer is simply 1.5 Weber. Remember, that is the SI unit of magnetic field. Yes or no? We got this?
Yes, sir.
Now, more often or not, you might be encountering question of this nature where you have a diagram with magnetic field and area vector. So this question could be put in different ways. In a given plane, horizontal and vertical components of Earth magnetic field are BH and BV. Along x-axis is the horizontal component. Along minus y-axis is your vertical component. What is the flux of Earth's magnetic field associated with an area S? If the area X, three cases are given, three different planes are given, X, Y, Y, Z, X, Z. I'll give you 2 minutes to tell me the answer for this one. I hope you know how to do it, right?
Yes, sir.
2 minutes. The answers are pretty simple. What you got to do, if we can't get the answer straight away, you can just write magnetic field in the I and J format. So it will be BHI minus BVJ. Then calculate the flux using B dot ds. You also write area vector in terms of vector quantity. In first case, your area vector is SK. In second case, it is SI. In third case, it is SJ. You just take the dot product in all the three cases and you will land up with your answer. In this case, flux is positive, and in this case, flux is negative. Do you all understand this?
Yes, sir.
Very simple. Might get a question on this type, and that is why I had done this. Let us now move on. There are more questions where you have to calculate the flux. This was simple because the magnetic field was uniform. There could be questions where the magnetic field is going to vary. We will see those questions once we get more into the problems. Right now, let us move on to Faraday's law of electromagnetic induction. Just give you a view of what is Faraday's laws of electromagnetic induction. I hope you know this, right? Whenever you have a magnetic flux linked with a coil, and that magnetic flux linked with the coil changes with time, then an EMF is induced in the coil. That is known as the Faraday's law of electromagnetic induction, and the value of that induced EMF is minus d phi by dt. Yes or no? It's equal to the negative of the rate of change of flux. This negative sign is given by the Lenz's law, is explained by the Lenz's law, which tells us the direction of induced EMF or the direction of induced current. Current will only come when the flux is linked with a closed loop. When the loop is closed, then only current can flow. The direction of induced EMF or the direction of induced current will be such that it will always oppose the change of flux. If the flux is increasing, it will try to decrease it. If the flux is decreasing, it will try to increase it. Do we know this, all of us?
Yeah.
So What matters is the change in flux at the rate at which it is changing. If it is changing fast, EMF is more. If it is changing slow, if it is changing at a slower rate, EMF would be less. How do you find the current in the circuit? Once you get the EMF induced, you divide it by the resistance of that circuit, you will get the current in the circuit. Do we all know this? Yes or no?
Yeah, yeah, sir.
You can also find out how much charge has flown into the circuit. To find out the charge flown into the circuit, you multiply the current with dt and integrate it. Once you multiply the current with dt, dt and dt will get cancelled, and the charge only depends on the change in flux. It does not depend on the rate. So whether you do it fast or you do it slow, charge flowing remains same. If you do it faster, current will be more. If you do it slower, current would be less. I hope you know this so that I can move ahead. Yes or no?
Yeah, yeah. Yes, sir.
Yes, beta?
Yes, sir.
Okay. Now, just to give you a brief thing about Lenz's law, how do you find the direction of induced EMF or direction of induced current? This is just a simple example of finding out the direction of induced EMF or direction of induced current. We are shown a current carrying wire and two rectangular loops, one loop moving along the vertical line along the wire, one loop is moving perpendicular to the wire, in which case EMF is induced, and what is the direction of induced EMF or induced current. You know how to do this? Yes or no? Okay. I'll give you 2 minutes to think about it and tell me the answer. So, how do you go about solving this? In first case, the loop is moving like this. Magnetic field due to infinite wire will remain same. The magnetic field is same and the distance is not changing. So there is no flux change. If there is no flux change, there is no induced EMF. So in this case, the induced EMF is zero. Yes or no? Do we understand this?
Yeah, yeah, yes, sir.
Okay. In the second case, this loop is moving away. If the loop moves away, the magnetic field as you go farther will become less. That means the flux is becoming less. It has to increase flux, so it will create magnetic field in the same direction as created by the wire. The wire is creating magnetic field in the downward direction, not downward direction, inside direction. It will have to create magnetic field in the same direction, and therefore it will have current coming clockwise, because when the current moves clockwise, magnetic field created by that current will be going in the inside direction. This is how you can apply Lenz's law and find out the direction of induced EMF, or for that matter, the direction of induced current flowing through the circuit. Do we understand this? Simple question, does not require much, right? But slowly, slowly, what will happen is the level of questions will go up. And this is the next question that I'm going to put. Remember, all the questions are simple because only simple questions come in a JEE. And this is the next one that comes. The ends of a search coil having 20 turns, area of cross section. Instead of taking turns as 20, you can take turns as n. Area of cross section as 1 centimeter square. Resistance is 2 ohms. Connected to a ballistic galvanometer of resistance 40 ohms. If the plane of the search coil is at an angle of 30 degrees to the direction of magnetic field, whose intensity is given, the coil is quickly pulled out to a region of zero magnetic field. Calculate the charge that passes through the galvanometer. Remember, they are not asking you the EMF, they are not asking you the current, they're only asking you how much charge has flown through the galvanometer. Again, a simple question. I'll give you 2 minutes to solve this one. I hope you understand the question. Yes or no?
Yes, sir. Just wait.
Very good. That is exactly correct. What you got to do is just find out the angle between the magnetic field and the area vector, which is 60 degrees. So you find out the initial
20
flux,
by 2 equal to yes, sir.
final flux is 0. You find out change in flux and you divide it by the resistance of the coil. And that's it. That's how you solve this question. Simple, isn't it? Yes or no?
Yes, sir.
Remember, all questions are simple unless otherwise stated. Comes this one. And again, this question, try to understand the language of this question and how you are supposed to do this. A current I is 3.36 into 1 plus 2t into 10 raised to the power minus 2 ampere increases at a steady rate in a long straight wire, a small circular loop, and that is the main point of this question. Of radius 10.10 raised to the power minus 3 meter has its plane parallel to that of wire, and its center is placed at a distance of 1 meter from the wire. The resistance of the loop is 8.4 into 10 raised to the power minus 4. Find the magnitude and direction of induced current in the loop. It's a very simple question, and I hope you can do it in the correct way. The more the number of questions you do, the more is the chances a similar question will come. I'll give you 2 minutes to solve this one. So how are you supposed to do it? Remember, it is a small loop, so you don't have to integrate and do anything. You just find the magnetic field at the center of the loop. Do you understand this?
Yes, sir.
U naught I by 2 pi a. You then multiply this by the area of the loop. Then you find out the EMF by differentiating phi with respect to time. So basically it will be something multiplied by di by dt, where di by dt is the rate of change of current. You just differentiate and find the rate of change of current, and you just put it in the final result. You will get the EMF. You divide it by the resistance R, and you will have the answer. You have this sheet with you, yes or no? You can have a look at the question from the sheet. So the answer will be simply 16 pi into 10 raised to the power minus 11 or minus 12. The book says minus 12. I think you can deal with that one. Okay. Well done. If you could do this one, then let me move on to the next question, and the next question is this one, and I hope that you can do this. Shown in the figure is a circular loop of radius r and resistance capital R, radius small r and resistance capital R. A variable magnetic field of induction B is equal to B naught e to the power minus t is established inside the coil. If key is closed, calculate the electric power developed right after closing the key. Again, a simple question. Just know EMF is minus d phi by dt. Minus sign only indicates the direction, so forget about the minus sign. Just do the needful, and I'll give you 2 minutes. Remember, these are the type of questions that are going to come. Simple. They might look a bit complicated, but they are simple. Okay, so how are you going to do this? As simple as everyone. You have to find out the induced EMF, which is d phi by dt. So this is d by dt of B into A. Area is constant here, so dB by dt into A. Pi r square into B naught into d by dt of e raised to the power minus t. So you get at time t is equal to 0, because it was given that right after closing the t. So you put the value of t as 0. You get the induced EMF B naught into pi r square. That was not the question, bacha. The question was to find out the power. I hope you understand what mistake you have made. Yes or no? You realize, bacha, what mistake you have made?
Yes, sir. Okay, sir. Clear.
You have only calculated the induced EMF, but that was not the question, beta. The question was to find out the powers generated. Got it? Can you move on to the next question then?
Yes, sir.
Here comes the next question. Again, a simple one. Now, you might think that this question comes from mutual induction. Big coil, small coil. But see the language of this question. Two concentric circular loops made up of wire of resistance per unit length 10 raised to the power minus 4. You can take it as lambda if you want to. You want to just solve it algebraically. Have diameters 0.2 and 2 meters. So one is D1, the other one is D2. A time varying potential difference 4 plus 2.5 T volt is applied to the larger loop. And that is how you are going to find the mutual inductance of the two loops. You flow current in the outer loop and you find the flux through the inner loop. Anyways, calculate the current in the smaller loop. Give you 2 minutes to deal with this one. It's a simple question, remember. Every question is a simple one. I hope you have understood how to do this. Magnetic field at the center of the smaller loop. Will be due to the current in the larger loop. It will be mu naught I divided by 2R. Yes or no?
Yes, sir.
Now this is potential difference divided by the resistance. Yes or no? So potential difference is 4 plus 2.5 T divided by total resistance of the loop 2 pi R multiplied by rho. Yes or no? So you can get the value of B which is created here. Are you getting my point, beta? Yes or no? This is the magnetic field created by the potential difference applied on the larger loop at the center of both the loops, the center of the smaller loop or the center of the larger loop. Are you getting my point, bacha? Have you understood what I have done?
Yes,
Magnetic
sir.
field at the center of the loop is mu naught I by 2R. Then I calculated current from the potential difference. Yes or no?
Yes, sir.
Okay. Now R is very, very small compared to capital R. That is how you find out the mutual inductance of the two loops. So you multiply this magnetic field by area pi R square of the smaller loop. You will get the flux in that loop. To find out the induced EMF, you do the derivative of that flux, and that is how you get the answer for the induced EMF. To find the answer for the induced current, you have to divide it by the resistance of the smaller loop. Once you do that,
Okay, sir.
you will have your answer. Do we understand this, bacha? If this question comes, it would not be so complicated. They will give you the answer in this form probably. Are you getting my point?
Okay,
Not
sir. Clear, sir.
not in terms of numerical values, because numerically the question looks quite difficult because there are numerical values associated with this. But our job here is to not do the numerical part. Our job is to understand the concept behind the question. Yes or no?
Yes, sir.
You got this, beta?
So half of I got, sir.
Shall I
Half
repeat?
of the part I got.
Shall I
Okay, sir.
repeat?
I can.
No, you have
Okay.
understood the question I have after I've explained it.
Okay, sir. I got it, sir.
Got it? No?
Uh,
You have to find out the magnetic field at the center of the loop, mu naught I by 2R, bada R, capital R, radius R. Find out the value of current by potential difference divided by the resistance of the bigger loop, and then you multiply it by the area of the smaller loop. Okay?
yes, sir.
Take you to the next question. This is somewhat difficult, and these are the type of questions which used to be asked when the JEE was very tough. To make a tough JEE this time, IIT Bombay can do that. This is the type of question that will come. It is a mixing of magnetic field, magnetic force, and rotation and things like that. So it becomes a bit tough. A bit tough if you don't understand the basics of it. Anyways, I'll put this question forward because this was the question I was supposed to do in the last class, but now is the time that I'm doing it. In a region of gravity-free space, there exists a non-uniform magnetic field. B is equal to minus B naught x cube K. So it varies along the x-axis. A uniform conductor, uniform means uniform cross section, everything is same. AB of length L and mass M is placed with its end A at the origin such that it extends along positive x-axis. Remember, no diagram is given. Find the initial acceleration of the center of mass. Wow, center of mass of the rod and of the end A when a current I flows from A to B. So I am making a current I to flow from A to B. This is not a question of EMI. This is a question of magnetic field and magnetic force.
Okay, sir. Okay,
Current
I
flows.
understood, sir.
I mean,
Question.
how this current flowing, sir? You will say, okay, sir, there's no loop, so current is not flowing. It's a question, right? So we are just finding out the uh, force on that loop, force on that rod. Do we understand this?
Yes, sir. I will do, sir. Wait.
So this question might interest you. Like questions like this interest me because they require understanding of mechanics, and that is why I'm doing this question. We give you 2 minutes to think about it, 3 minutes to solve it. Okay then. Remember, magnetic field is going inside and it is varying with x. So all the elements will experience different forces. Though the direction of the force, if I take dl cross b, all the forces will be along the positive y-axis. Dl cross b, dl, b is inside. All the forces will be in the same direction, but they will be of different magnitudes because magnetic field is varying. Do we understand this? All the forces would be in the same direction, but they would be different. Yes or no? So if I find out the force on a small section, it would look like this. It will be along positive j axis. Yes or no?
Yes, sir.
So the total force on the rod, all the forces will add up, will be the integral of this. If I find the integral of this, it will be b naught I L raised to the power 4 by 4. Then I can find the acceleration of center of mass. The total force divided by the total mass will be the acceleration of center of mass. Yes or no?
Yes, sir.
This question would have been ending here. It would have been a relatively simple question, but this rod not only moves translationally in translational motion, it also rotates and it has an angular acceleration as well, because all the forces are not equal. Forces are different at different points, and therefore they will create a torque. And a body which is free to rotate, remember this, if a body is free to rotate, there is no hinge. The body is free to rotate. About which point will the body rotate? Will always rotate about the center of mass. Yes or no? No, yes. Do you understand this?
Yes, sir.
This rod is going to rotate. Now I have to find out what is the angular acceleration of rotation about the center of mass, because it is going to rotate about the center of mass. So what do? I take any force at a distance x from the end A, and I find the torque of that force about the center of mass. So distance of that point from the center of mass will be x minus L by 2. I'm assuming that the point is on the other side of the center of mass, multiplied by the force dF. That will be the small torque that I get. Are you getting this point, beta? The torque.
Yes, sir.
That is the most important aspect of this question. Then I can find out the net torque. I will find the net torque by integrating it from 0 to L, and this will be the net torque along the K axis. But remember, the question does not finish here. Do we understand up till this point, beta?
Yes, sir.
The question does not
Yes, sir.
end here, because I have to find the acceleration of a point. Now, if I have to find out the acceleration of a point, I will have to apply that formula. What formula? The acceleration of any point, acceleration of any point will be acceleration of center of mass plus alpha multiplied by the radius vector of that point with respect to the center of mass. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
That's it. So once you get the torque, you divide it by the moment of inertia of this rod. You will get the angular acceleration of this rod. Then you will have to apply this formula, and from there you will get the acceleration of the point A. This is a difficult question because at any point if you make a simple mistake of any plus or even a minus, your final answer would look drastically different. Do we understand this better?
Yes, sir.
Have you understood the question how it is done?
Yeah.
First of all, you find out the total force acting on the rod divided by the mass of the rod. You will get the acceleration of the center of mass. That is the simpler part. Yes or no?
Yes, sir.
But then you'll have to also find the angular acceleration. To find out that, you have to find the small torque. All the forces will have different torques. Find the total torque divided by the moment of inertia, you get angular acceleration. Then you have to find the acceleration of point A. Using vector laws, you find that acceleration. Can I move ahead?
Yes, sir.
Okay. Now let us move and see in how many ways you can change the magnetic flux. Remember, the simplest formula that I have created for magnetic flux is BA cos theta. Yes or no?
Yes, sir.
BA cos theta. Why I am written phi and phi will get confused. So BA cos theta, where B is the magnetic field, A is the area, and theta is the angle between B and A. Yes or no? Now I can change flux by changing any one of these quantities or any two of these quantities or all three of these quantities. Now changing any two or changing any three, you will hardly get a question. But what questions do you normally get is we are going to change any one of these quantities. Are you getting my point, beta? We are going to change either B. In that case, we don't move that object, and we still have induced EMF in the coil. That type of EMF is known as static EMF or static EMI. It is due to a concept of induced electric field. We will deal with this concept at the very last. Induced electric field. This is explained by the concept of induced electric field. Or you can change the area of the coil. That means you are going to move that coil, move something. This type of EMF or EMI is known as dynamic EMF or dynamic EMI. We explain this EMF by the concept of motional EMF. Do we know this concept of motional EMF? Have you heard this concept of motional EMF, beta? Or you can have the third thing, you can have an angle changed, and this is known as periodic EMI. And this is how most of the current that comes at your home is created. You have a fixed magnetic field and the area of the coil does not change. What you do is you keep on rotating that coil, and you have a AC generator which generates your alternating EMF or alternating current, which of course is your next chapter. Do we understand this? Yes or no? Are you there, beta? Do we understand this? Have I lost you? Are you there in the class, beta? So the first case is where we are going to change the area of the coil. And how are we going to change the area of the coil? We are going to move a conductor inside a magnetic field, and this EMF can be explained how this EMF is generated or how this induced voltage is generated. We can understand it by the concept of motional EMF. You must be knowing this concept of motional EMF, yes or no?
Yes, sir.
So what we do is we just replace this moving conductor by a battery whose EMF is BVL. Yes or no?
Yes, sir.
So we just replace this moving conductor by a battery whose EMF is BVL. Yes or no?
Sir, not yet, sir.
You know about motional EMF or not?
Yes, sir.
Yes. So basically what you do in motional EMF is you will have a conductor which is moving with a velocity v inside a magnetic field B. A conductor of length L will move like this, and what you are going to do is we are going to replace this conductor by a battery. Yes or no?
Yes, sir.
The EMF of this battery will be equal to BVL. Yes or no?
Yes, sir.
How do you find out the positive terminal or the negative terminal of the battery? You do V cross B, V cross B. Wherever your fingers point, that point becomes your positive terminal and the other point becomes your negative terminal. Do you understand this?
Yeah, yes, sir.
This is known as your concept of motional EMF. So wherever you find something moving, you will always try to apply the concept of motional EMF. In fact, if I write it more methodically, this induced EMF can be written as integral of, should not write it as line integral. This is integral of V cross B dot dl. Do you know this
DL, yes,
formula?
sir.
This is a scalar triple product. Yes or no?
Yes, sir.
And the scalar triple product becomes zero if any two vectors are parallel. Yes or no?
Yeah, yes, sir.
So if any two vectors become parallel, this motional EMF will become equal to zero. Yes or no?
Yeah, yes, sir.
Okay. Then you can solve very simple questions and remember all these cases, because whenever a question comes in a JEE, it will be coming from one of these cases which are not in the sheet that I have given to you, but you can just note it down. If your magnetic field B and V, or V and L, or B and L, any of these two things are parallel, the induced EMF is going to be zero. Yes or no?
Yes.
So remember this case. So that means if I give you another good example, if I have an infinite current carrying wire, and if I have another wire which is moving like this with a velocity v, the length of this wire is L, what will be the induced EMF across the ends of this wire? See, magnetic field is going inside, V and B are perpendicular, but look at this V and look at this L. This V and L are parallel, yes or no?
Parallel. Yes, sir. They are parallel.
Therefore, the induced EMF in this part will be zero. Are you getting
Zero.
my point, bacha?
Yes, sir.
But if this wire, instead of moving like this, if I move the wire like this, then you will have induced EMF across the two ends of the wire. Are you getting my point, bacha?
Yeah, yes, sir.
So remember, if any two vectors VL, BL, or LB are parallel, the induced EMF becomes zero. A very important point that you should remember. Looking at these two cases, again, as you can see here, this was the case that I was trying to tell you. V and L here are parallel, yes or no?
Yes,
And
sir.
therefore the induced EMF is zero. In this case, B and L are parallel, and therefore the induced EMF is zero. Are you getting my point, bacha?
Yes, sir.
Now, Another very important concept that is going to help us in solving a lot of questions. If you have a closed loop which is moving inside a constant magnetic field, if you have a closed loop moving inside a constant magnetic field, then whatever happens, the area of this loop is not going to change, so there will be no flux, no change of flux, and therefore the EMF induced in this entire loop would be zero. Do we understand this?
Yeah, yes, sir.
Induced EMF in this entire loop is zero. That means whatever EMF is induced in this curved path, the same EMF will be induced in this straight path. Yes or no?
Yes, sir.
That means if I have a random shape loop AB which is moving in a magnetic field, and if someone asks you what is the EMF induced in this loop, what you got to do is do the same thing that we have done. We are going to close this loop. Are you getting my point, bacha?
Yes, sir.
Whatever EMF is induced in this curved part, the same EMF would be induced in this line wala part. Are you getting my point?
Yes, sir.
So instead of finding out it directly on this curved path, we will just find it out in the straight path. This will save you a lot of time in questions that can come, because question can be pretty straightforward like this. The similar question that I have made, what is the EMF induced in this irregular shape? So what you got to do is you just join these 2 points and then you have velocity v like this. Yes or no?
Yes, sir.
But remember, if you have a straight wire and you have a velocity like this in a magnetic field which is going inside, and the length of the wire is L, how do you find out the EMF induced in this rod? The velocity is not perpendicular. So what you do in this case is you break down this velocity into two components. This is not a good color to use. You break down this velocity into two components. One is V perpendicular and the other one is V parallel. Are you getting my point, beta?
Yes, sir.
This V parallel component of velocity is not going to produce any induced EMF because V and L will become parallel. So the induced EMF will only be due to this perpendicular component, and you can write it as V perpendicular into L into B. That would be the induced EMF in this part. Are you getting my point, bacha?
Yes, sir. Yes, sir.
Okay. How do you find out which is the positive terminal and which is the negative terminal? So you do V cross B.
Direction.
Your point A will become your positive terminal and your point B will become your negative terminal. Is it clear?
Yes, sir.
So this will cover almost all types of questions that are going to come for you. Now this is a simple problem here. If you can tell me what is the induced EMF in this case so that I can move forward ahead. It's a very simple problem. Does not require much understanding.
Yes, sir.
Find the EMF.
It is in parallel, no, sir.
So the answer would be?
0.
The answer would be 0. That is correct. What is the answer in this case then? Which is the point with the higher potential and which is the point with the lower potential? Where is the positive terminal? Where is the negative terminal in this case?
Oh.
I'll give you 2 minutes. So it is a very simple question. What you got to do? The easiest way is to close this loop. Whatever EMF is induced in this part, the same EMF will be induced in this part, and the EMF induced in this part will be 2B into R into V. Yes or no?
I go, sir. To be
You
R
just
into
close the loop. And velocity is here, velocity is upwards, magnetic field is downwards. Point P,
if it is downward also same, no, sir?
yes, point P will be here and point Q will be here, and the EMF will be equal to 2BRV. Do we understand this better?
Yes, sir.
Yes or no?
Yes, sir.
Got it? Then this is a small question just to make you understand that if you have a loop, now remember, if you have a full loop moving inside a constant magnetic field, the EMF induced in the entire loop would be zero. Yes or no?
Yeah.
But here they are asking what is the EMF induced in each and every segment. So you have to find out the each and every part, PQ, QR, RS, and SP. You can take the length of PQ as L, and you can take the length of RQ as B, so that you can understand how they are going to get cancelled. I will give you 2 minutes to do this. See, it is very simple, right? This part and this part, they are parallel to velocity, so there is no EMF induced in these two parts. Yes or no?
Yes, sir.
This part and this part, they are perpendicular,
Perpendicular to velocity.
PLV. But if you take the entire loop, the net
Loop.
EMF in the loop will, both the batteries will cancel out each other, and therefore you have net EMF induced as zero. Do we get my point?
Yes, yes, sir.
Okay. So that is how you can do this. Now let us move on to a question where you might not have uniform magnetic field. And what will happen in this case? So this is the simplest possible case. You have a rectangular loop as shown in the figure moving away from an infinitely long conducting wire. Find the EMF induced in this loop. The length of the loop is L, the breadth of the loop is B. These are the distance X from the wire. What is the EMF induced in the loop? Remember, whenever you see something moving, the angle is not changing, but something is moving. That means that is a question of motional EMF. And I'll give you 2 minutes to solve this. Okay, so how are we supposed to do this? As you already said, that in two of these wires, and mark it by red, this wire and this wire, the magnetic EMF is zero. There is no EMF induced because this part and this part are parallel to V. Yes or no?
Yes, sir.
So now I'm left with these two parts, part A and part B. Do we understand this, bacha?
Yes, sir.
Now, in part A and part B, the problem is magnetic field is not same. So therefore, I've written it as B1 and B2. Yes or no?
Sir, why
The
magnetic
value
field
of,
is not same, sir, in that?
yeah, the value of B1 is mu naught I by 2 pi x. Yes or no, beta?
Yes, sir.
And the value of B2 is mu naught I by 2 pi x plus B. This is greater and this is smaller. So we subtract the smaller from the bigger one. Are you getting my point, bacha?
Yes, sir.
And that is how you get, once you subtract, that is how you will get the EMF in the entire loop. Two parts cancel. EMF in the two parts is zero, but the other two parts are there. Do we understand this better?
Yeah, yes, sir.
Okay. Do you want to note it down?
Yes, sir.
Please note it down because a question comes from this. I'll give you time. Then we move on to the next question. Now in this next question, what I have done, I've just taken one wire and I am moving it with velocity V perpendicular to it. This is kept in the magnetic field of a infinite wire at a distance A. The length of the wire is A, L, And now you have to find out the EMF induced in this wire, only one wire. Are you getting my point, beta?
Yes, sir.
Okay, so I'll give you 2 minutes to do this, and you will have to remember the results because a question of this nature would definitely come if it comes in EMI. You have to remember the results. Great, so I think that is correct. What you got to do is you move a distance x, then you take a small element of length dx. Are you getting my point?
Yes, sir.
Find out the small EMF induced in that part. V naught I by 2 pi x, that is the magnetic field, into V into dx. You just integrate it from A to A plus L, and this is the answer that you will get. Yes or no?
Yes, sir.
It is very simple. Remember, this is the EMF induced in this small segment. Now, if I make the question like this, where you have this entire loop here, now what will be the answer of EMF induced in this entire loop? Now, you can apply some common sense and you will be able to give me the answer.
Just wait, sir.
We've done this question before. That is the first question that we discussed when we discussed what will be the direction of induced current or direction of induced EMF. And then you said that the EMF induced in this part, this entire loop is going to be how much? It will be zero. Yes or no, bacha? Because the flux is not going to change. It is moving parallel to the wire. Yes or no?
Yes, sir. I will do it, sir.
Remember, this part and this part, there is no induced EMF because velocity is parallel to the length. Yes or no?
Yes, sir.
Whatever EMF is induced in this part, you have just found out that value. Same EMF will be induced in the lower part, and both the batteries will cancel out each other. Are you getting my point, bacha?
Yes, sir.
So it will look like this, my dear friend. You just calculated the value. Yes or no, beta? Will look like this. Yes or no?
Yes,
Do
sir.
you
Yes, sir.
agree or not?
Okay.
Do you agree, beta?
Yes, sir.
Full confidence you agree. Yes or no?
Yes, sir.
That is why the entire loop, the EMF is zero. Shall we move ahead?
Okay, sir.
Now, instead of things moving, if you have a rotating rod like this with an angular velocity omega of length L, you just have to remember that this is the induced EMF half B omega L square. How do you get it? You find out the small EMF induced in the small section here. I hope you know this. Yes or no, beta? That small EMF in this small portion will be B omega R dr. You integrate this from 0 to L and you get the EMF induced in this entire rod from O to A is B half B omega L square. How do you find out the direction of induced EMF? You take out the velocity V cross B. So your outer end will be at a higher potential and your inner end will be at the lower potential. Do you understand this? Getting
Yes,
my
sir.
point? V
Yes.
cross B. In all cases, to find out which is the positive terminal or the negative terminal, you are always going to do one thing and one thing only, that will be equal to B cross V cross B. Yes or no? No, yes.
Yes, sir.
I hope you don't make a mistake in this. Then there is a small problem based on this. A rod PQ of length 2L is rotating about point P in a uniform magnetic field which is perpendicular to the plane. Find the induced EMF or the potential difference between the point M and Q. If between P and Q, the potential difference is given as 100 volts. Remember, this is how questions are framed in a JEE. Questions are simple. You understand them. I'll give you 2 minutes to solve it. Yes, I think you got the correct answer. 75 it is. And how are you going to do this? It is pretty damn simple, beta. Remember, you know the induced EMF between the two ends, the center and the end, yes or no? Now, instead of taking the length as 2L in the solution, it is given as L. So, between P and Q, you know the induced EMF is half B omega L square by 2, yes or no?
Yes, sir.
Now, between P and M, which is half of the length of the rod, you can just replace L by L by 2 and you can get the induced EMF between P and M, yes or no?
Yes, sir.
Induced EMF between M and Q plus induced EMF between P and M will be equal to induced EMF between P and Q. From there, you can calculate the induced EMF between M and Q. Did you get it better correctly this way? Yes or no? No, yes.
Yes, sir. Yes, sir.
Well done. That means you are picking up the topic. That is great. Again, this question comes instead of taking the length as 2L, take the length as L. A rod PQ of length L is rotating about its midpoint C in a uniform magnetic field which is perpendicular to the plane of rotation. Oh, you can take the length as 2L here only because I think this is solved by 2L. Find the induced EMF between P and Q and P and C. Draw the circuit diagram of the part PC and CQ. Give you 2 minutes to do this. So how are we going to solve this question? This is pretty straightforward and I hope you get it.
Yes, sir.
This is the point C. You can easily find out the potential difference between C and Q. It will be half P omega L square because C to Q is L. And if I take V cross B, point C will be at a higher potential. Yes or no? You got this part, bacha?
Yes, sir.
Similarly, if you draw the equivalent battery between P and C, again point C will come at a higher potential and the potential difference between P and C will be B omega L square by 2. That means point P and Q, which are the two ends of the rod is not rotating about end, it is rotating about the center point. Are you getting my point, bacha? Yes or no?
Yes, sir.
Point P and Q, which are on the ends of the rod, they are at the same potential. Are you getting my point?
Yes, sir.
Got it, beta?
Got it, sir.
Now, this question could have been put in a different way. Instead of a rod, you could have a ring. You could have a ring of radius r rotating with an angular velocity omega. And now they can ask you what is the potential difference between the center and any point on the circumference of the ring. What is your answer now? Instead of the rod, if I make it a ring, what is the answer now? Between the center and any point on the surface of the ring, on the circumference of the ring. Remember, the answer is still same, half B omega r square. Do you understand this, beta?
Yes, sir.
And again, how do you find out the higher potential? V cross B. So in this case, if the magnetic field is going inside, point O will be at the higher potential. Are you getting my point?
Yes, sir.
Then they make one more point on the circumference of the ring and then they ask you what is the potential difference between A and B. Then what would be your answer? What would be the potential difference between A and B? 2 points on the circumference of the ring. What will be your answer?
Uh,
The answer would be 0. Are you getting my point, beta?
0.
Are you getting my point, beta? 0. The answer would be 0. Yes or no?
Yes, sir.
Now, instead of a ring, they make it a disc. So this is all filled with metal. Are you getting my point? They make it a disc. And now they ask you, what is the potential difference between these 2 points, this point P and this point Q. Now remember this point P and this point Q. This question is similar to the question of the rod that we had done between M and Q. Remember that question, beta?
Yes, sir.
Do you remember that question? So this question and the previous question where we had calculated the potential difference, both the questions are similar now. So whether it's a rotating disc or a rotating rod or a rotating ring, the question remains same. Do we understand this, beta?
Yes, sir.
Yes or no? No, yes.
Yeah, yes, sir.
Got it?
Got it,
Then
sir.
I will give you one question that you will try as homework. And this is the question where now I've changed the scenario. I still have a rotating rod with a constant angular velocity omega, but now it is placed in a non-uniform magnetic field. And remember, wherever you have an infinite wire, the only reason an infinite wire is given in a question is to create a non-uniform magnetic field. So now this question says a rod of length L is rotating with a constant angular velocity omega. Its one end it has a distance a from an infinitely long wire carrying current I. Find the EMF induced in the rod at the instant where the rod is horizontal like this. Can you solve this question for me?
Yes, sir.
Yes or no? No, yes.
Yes, sir. I will try, sir.
Okay. So you try this question at home while you are preparing for it. In today's class, we have tried to discuss the concept of motional EMF and try to do some very interesting problems. One or two problems still are left, so we will be covering them in the next class. More problems based on this changing of angle between B and A that we'll cover. Then we will go into the concept of induced electric field, and then we'll move on to induction and inductance. So we'll try to wrap it up in one or maybe two classes.
Okay,
EMI
sir.
would be wrapped up. We'll go slowly because I want you to get confidence in this. I hope you have gained some confidence in this concept of motional EMF. Yes or
Yes,
no?
sir. Yes, sir. Yes, sir.
You have the sheet with you, the second sheet. There would be questions on motional EMF. Try them. Okay. If you have any doubt, you can always ask them. I will try to go slow and cover this topic in two more classes from today. So I'll wind up this class here today. Take care and have a nice day, beta.